Thank you very much for sparing your valuable time to join today's session. My name is Thomas Pascal from the ITU. The AI and Machine Learning 5G Challenge is organized by the ITU, which is United Nations Agency for ICTs. The mandate of the ITU is to allocate frequencies to services that uses the radio spectrum, to develop standards, and to assist developing countries in setting up their ICT infrastructure. This challenge is kindly sponsored by Xilinx, and we are grateful to Xilinx for their sponsorship. The challenge aims at creating a community that will solve network-related problems using artificial intelligence and machine learning. Before we get started, I would like to go through a couple of housekeeping rules. On the bottom panel of your screen, you'll find two icons, chat and Q&A. If you have questions that you'd like to ask the speaker during the presentation, please type them in the Q&A window. For any other type of communications, use the chat window. Also note that all attendees, their microphone is disabled. And also please note that we are recording this session, and we will provide this the recording as well as the PowerPoint slides at the end of the webinar on the challenge website, as well as on the event page. Now it's time for me to introduce today's speaker. Today's session is going to be, today's presentation is going to be done by Professor Christos Massoros. He received the diploma degree in electrical and computer engineering from the University of Patras, Greece in 2004, and MSc by research and PhD in electrical and electronic engineering from the University of Manchester, UK in 2006 and 2009, respectively. In 2008, he was a research intern at Philips Research Labs, UK. And between 2009 and 2010, he was a research associate in the University of Manchester. And between 2010 and 2012, a research fellow in Queen's University, Belfast. In 2012, he joined University College London as a lecturer. He has held a Royal Academy of Engineering Research Fellowship between 2011 and 2016. Since 2019, he's a full professor of signal processing and wireless communications in Information and Communication Engineering Research Group, which is under the Department of Electrical and Electronic Engineering, which is affiliated with the Institute of Communications and Connected Systems, University College of London. His research interest lies in the field of wireless communications and signal processing, with particular focus on grain communications, large-scale antenna systems, integrated sensing and communications, interference mitigation techniques for MIMO and multi-carrier communications. He was a recipient of several Best Paper Awards in IEEE conferences. He has been recognized as an exemplary editor and reviewer. He is an editor for several IEEE journals, as well as being an associate editor of IEEE communications letters and guest editor for a number of IEEE journals. He is also a founding member and vice chair of the IEEE Imaging Technology Initiative on Integrated Sensing and Communications, vice chair of the IEEE Special Interest Group on Integrated Sensing and Communications, and the chair of the IEEE Special Interest Group on Energy Harvesting Communication Networks. In today's talk, he's going to present an overview and technical highlights of the project LeanCom, which is learning to communicate deep learning-based solutions for the physical layer of communications. This is going to be on AI-inspired physical layer wireless communications. The basis of research is the advancement of signal processing for physical layer wireless communication design, which is going to address complex scenarios where classical signal processing approaches underperform. So we are looking forward to this interesting talk. I would like to welcome Professor Chris. Good morning.
So thanks again for inviting me, and thanks everyone for attending today. Hello from my side as well. So this talk is going to be about, the topic is learning to communicate. So, you know, our own research in the areas of applying deep learning to communications design, communication systems design, and communication problems. It's not going to be about, you know, how communications can assist deep learning. There's a lot of research on that, like federated learning and so on. I'm going to be focusing, and you probably heard some of that, I think, in previous seminars, and in the next few seminars you might hear some of that, but I'm going to focus on how deep learning can assist in the design of communication networks. With that, I'd like to set the context a little bit of this talk. So talking a little bit about, you know, what is the use of deep learning, at least in my view, on communication networks. What are the key challenges that I see that are particular for communication networks? And what are the opportunities for communication networks as opposed to other disciplines like computer vision, where deep learning has been used a lot. So why deep learning for communications? So the uses that I've seen, and they are widely acceptable, are to address mathematically non-tractable problems. So these can be problems where either you don't have an accurate model for some physical phenomenon, so you don't really have any maths to base your design on, or you have models that are too complicated to be able to tackle mathematically or with classical signal processing approaches. So the key idea here is to use learning-based approaches instead. The other aspect is when you, let's say, have a good model and you have a known solution that performs well, then using learning-based approaches to reduce complexity or make it more practical for implementation. So these are the 2-3 areas that we're interested in as part of this project that Thomas mentioned. And the particular challenges that we see in applying deep learning in wireless communications, first of all, is the need to tailor neural networks and deep learning architectures to communications. So use bottom line communication metrics as opposed to, let's say, computer vision metrics. So this means new loss functions, new architectures of neural networks, and so on. The other key challenge is the limited online training. So if you think, let's say, of computer vision or image processing or classification of images, you have all the time, let's say, in the world to train a neural network and be able to classify images. While in communications, you often have dynamic environments, dynamic changing topologies, changing channels. So training and retraining a neural network has to be efficient with minimal overhead. So that's a key challenge that we think is important in this area. And the other thing is the complexity of these neural networks and being able to deploy these in small devices with limited capabilities. So we think it's interesting to look at implementations of neural networks that are lightweight, consume limited memory, have limited complexity, and are hardware friendly. So they're not agnostic to the hardware implementation. There are some key opportunities in the communication domain. So again, unlike computer vision, where probably you don't have any good analytical models to design your solutions, here in your communications, we spent 5 generations of networks from 1G to 5G to designing a model-based solution, either optimal solutions or heuristic solutions that perform well. So it would be a waste to start designing everything from the start with replacing everything with neural networks. You can actually develop hybrid model-based and data-driven approaches using the knowledge that we built so far. So I'd like to acknowledge, this project that Thomas mentioned, so LeanCom, so that stands for Learning to Communicate and Applying Deep Learning Approaches to Physical Layer Communications. This is an EPSRC, so a UK national project. It's already in its second year. And it's with my colleagues, my esteemed colleagues in UCL, in the Department of Electroengineering, Miguel Rodriguez, Izzat Darwaze, and Yannis Andreopoulos. And in response to these opportunities and the context that I said in the previous slide, the aims of this project are to establish a deep learning framework that is tailored for wireless communications. So borrowing concepts of other disciplines and tailoring these for communications. To come up with physical layer transceiver design based on neural networks, so replacing classical blocks in the transceiver chain with neural network implementations. And also to design hardware-informed and hardware-efficient deep learning transceivers that take into account practical effects. And we'll see some examples in the next few slides. And towards the end of the project, we want to be able to demonstrate some pockets of capabilities or some small proof of concept experiments of deep learning based communications. So this is what I'm going to be talking about today. Hopefully I have enough time to go through all these. So I'm going to be presenting you some snapshots of research that we've done as part of this project, some technical highlights that also represent application examples where we think deep learning is interesting to apply for communication scenarios. So I'll be looking at deep learning for relaxing channel state acquisition and making this more efficient and reducing overheads. Deep learning for designing hardware-friendly or implementation-friendly neural networks. Deep learning for radar-assisted vehicular networks. So this is a new area of integrating radar and communications and how deep learning can be applied to vehicular scenarios. And I'll go very briefly through the last 2 points of deep learning for fixed wireless access links and learning solutions for joint precoding and CSI specification. So making, again, joint designing of precoding and relaxing your CSI acquisition. And I'll end the talk with highlighting a couple of specific topics where I think there's plenty of opportunity to apply deep learning. And these will be on net zero energy communication, so energy autonomous, let's say, wireless networks, and in the area of integrated sensing and communications. So first, a bit of highlights. I'd like to talk to you about a solution where we looked at a complex problem and we tried to relax a system design from being fully CSI based, so having to acquire CSI, to reducing that to just location-based data-driven transmission. So we've chosen a rather complicated scenario. So let me spend a minute or two to explain a little bit the scenario. So you have a number of user equipments here that have a computational task. So this is part of mobile edge computing and assisted by reconfigurable surfaces. So you have a number of users that are limited, have limited energy and battery remaining, and want to carry out some computational tasks. So the key here is to part of the task compute locally, so at the user, and part of the task offload to a nearby access point, which is connected to an edge server that can do the computation for the users. And the task can be some complicated tasks like, I don't know, computer vision or image processing, or even training a neural network. And that's assisted by a reconfigurable intelligent surface. And these, for those of you who might not be familiar, these are very briefly a large number of typically passive elements that act as reflectors, and you can modulate the signal and actually convey information by changing the phases of these reflectors in the most typical implementation. So the key idea here is to use a learning-based approach to basically design this complicated scenario. And you'll see in a minute that this involves designing the computational partition at the users, designing the elements at the reflecting surface, and designing the combining for communication at the access point. So it's rather a complicated scenario. And we want to reduce complexity. This is our first aim. The second aim is to reduce the overheads in acquiring all this involved channel knowledge and coming up with a solution that's based on only on location information. Apologies if some noise is coming out from out where we're close to a hospital here, so we tend to get a bit of noise. So back to our technique here. I won't go through the math in much detail. The key points here are bearing in mind the scenario. The key idea is that these guys over here, the users, are limited in their available energy, and they have a total energy available noted by E over here. For the nth user, you have this amount of energy. The key idea is for the users to decide how much of the computation they can do locally with their processor, how much they want to offload to the access point. And this will be represented by this coefficient here. For the nth user, alpha will tell you it's a constant between, it's a factor scaling between 0 and 1, and will tell you how much of the computation the user will do offload. So offloading is part of this energy, this part of the energy, and doing local, the rest of the remaining energy they will consume in doing their local computation. So that's one parameter you want to tune here for each user. Then you have the RIS coefficient matrix, or the reflecting surface coefficients, which are phase only. And then you have the combining WN over here for each user at the access point. And you can, find the received signal of that access point. I won't go again through too much detail. The important bit is that this depends on the 3 channels here. So the channel from the users to the RIS, from the RIS to the access point, and the direct channel from the users to the access point. And the main thing you're tuning here, as I said, is the combiner at the edge server. So you want to offload part of the task bits. So we call them task bits. So the performance here is measured in completed task bits. So how much of the bits, how much of the computation you manage to carry out. And you have the offloaded bits, which are basically a function of the rate you can achieve to transmit the information to the edge server, times the bandwidth, obviously, and the time it takes to transmit, or the time you have available to transmit. And you want to somehow maximize this through the design of the partition, the RIS coefficients, and the combiners. And then you have the local computing, locally computed bits, which are just a function of how much of the bits you want to keep local, and then the computational capabilities of your local processor. So this is more or less the setup of the problem. And a typical optimization problem here involves maximizing the number of bits that you basically compute. So the sum of the offloaded and the local bits. And then here, you're optimizing 3 things. And that's where the learning-based approach becomes interesting. Under the constraints that these coefficients, the energy partition coefficients, can be anything between 0 and 1, either doing everything locally or doing everything offloading everything to the edge server, or anything in between. And the coefficients of the reflecting surface being unit amplitude, so phase only reflection coefficients. This is a non-convex problem, difficult to solve. You can come up with optimization solutions, and that's what we've done as a first step in this work. But the idea is you're designing 3 things at once, right? So at 3 different places at once. And this can be solved by optimization techniques. One classical one is breaking this into sub-problems, so optimization problems, and iterating between solutions. And we've seen that if for a given pair of coefficients A and phi, you can find W in closed form, and that kind of reduces complexity already in the way you optimize your solution. And this can be solved by classical model-based techniques with alternating optimization and block coordinate descent. I won't go into the details, but they're already there in the relevant paper. What's the problem here? The problem is that this block coordinate descent solution is rather complex. It guarantees a good performance, and we'll see indicative results in a minute. But its computational complexity grows with a number of RIS elements and with a number of users, and it grows significantly. So with the sixth power of k, where k is the number of elements, and this is typically a large number, so hundreds of elements, and with the 3rd power of the numbers of users. So very quickly, this can become a very complicated problem. So we want to use here deep learning approaches to reduce the complexity as a first step. And as a second step, as I mentioned already, we want to use learning-based approaches to relax the CSI acquisition from full CSI acquisition, where here, again, there's a challenge of needing to know 3 different channels over here, to coming up with solutions which are based only on the location of the users here. And we look at 2 main scenarios for which we designed the 2 different techniques. So we're looking at a scenario where we have a weak line of sight link from the users to the access point, maybe blocked. And we have non-line of sight paths dominating the channel. Or the case where you have a combination of non-line of sight, but with a strong line of sight link. And here's where we design the 2 solutions, one based on channel coefficients. So an architecture based, so deep architecture based on coefficients. and one where we basically extract the correlation between the location and the line of sight channel to design a location only based solution. So obviously this has significant gains in removing all this parallel channel estimation, the feedback, the quantization that's involved, and so on. And the other thing we take into account is imperfections and uncertainties. First of all, in the channel, the CSI, when we're looking at the CSI-based solution, but also in the location and the knowledge about the user's location when we look at the location-only approaches. So first bit of results is that of complexity. So remember, our first aim was to reduce the complexity of the solutions. And here we have, in the first graph, we have the complexity of the optimization-based algorithm. And complexity here we measure in terms of the running time. So we use the same CPU for all the techniques. And you can see that as the number of user grows, it can take up to, let's say, 60 seconds to solve the optimization problem that we saw in the previous slide. What is the big gain here? Already with step one, we have a massive reduction in the computational time to solve this optimization. So this is the result for the CSI based for the two scenarios, line of sight and non-line of sight. And this is the result with a location only based approach. Again, line of sight and non-line of sight. And you can see from the order of seconds, we're down to the order of microseconds. So about 10 to the 6, so 1 million times faster than the classical optimization based approach. So that's a key benefit by using this learning based approach. The second benefit, as I mentioned, is reducing the need for CSI and basing only on location information. And here we compare the performance. Our key metric here is the total input bits that we managed to compute. And we look at this with increasing numbers of antennas at the access point. These are some benchmark techniques. So zero forcing techniques, equal energy allocation, or direct offloading. So pushing everything at the access point without the intelligent surface. And this is what you get in our scenario with the optimization-based approach and with the learning-based approach. So that you can see here we show the scenario without a line of sight. So we compare the optimization-based approach, so the classical approach, with the deep learning-based approaches, the one with perfect CSI and the one with uncertainty in the CSI. And you can see a very close match in terms of the bottom line performance here, right? But as you saw before, with a much reduced complexity, maybe a million times less in terms of the online complexity. And here we have a scenario with a strong line of sight, where there's significant correlation between the position, the location of the users, and the actual channel response. And here we include the results for the location-only based approaches. So these lines correspond to the optimization based, so the top line, so the classical approach, the one based on CSI that closely matches that, and the location based, which performs within, let's say, less than 5% distance from the optimum. Again, here, once again, I'd like to highlight the complexity reduction. That's the key for using deep learning in this scenario, and the reduction in the overheads in acquiring CSI when you replace the processing with something that comes up with a solution only based on location information. So that was the first area where we think learning-based approaches can give you some real significant breakthroughs. The other topic that I want to talk about is the study about taking hardware implementation or implementation of the neural networks into account. And I'm going to talk about two things here. So first, I'm changing the scenario a little bit to a simpler one. So here we're looking at a simpler scenario where we have a transmitter and a receiver. It could be point-to-point. It could be also uplink multi-access scenario where you have a number of users transmitting to a receiver. And we're focusing on the receive processing here. So here we have the signals transmitted from the transmitter through the channel And our aim is detection, replacing detection with a deep learning based approach. So classical detection approaches, we have plenty. So from maximum likelihood, optimal detection, sphere detectors, successive interference cancellation, or low complexity linear approaches. But we want to come up with a learning based approach that replaces, these approaches. The key here that we want to look at is what happens when you start, when you look deep into the implementation of the neural network. So that if this is the neural network, it will have a bunch of layers. I won't go into the details of the architecture, but the key message here is we want to reduce the the complexity of the neural network and the memory footprint of the neural network, so the memory I consume, by dropping non-significant weights in the neural network. And looking at not the performance of the neural network on its own, that's something that you would do, let's say, for computer vision, but looking at the bottom line communication performance. So how does dropping weights, so neural network weights, affect the bottom line communication performance? So first of all, we've seen in the results that I don't show here, but you can have a look in detail at this paper. We've seen in the results that, first of all, the neural network implementation performs very closely in terms of bit error rate and overall performance to sphere detection algorithms, so classical high complexity algorithms close to optimal algorithms. And then secondly, the main message is in this figure here. Here we show the bit error rate with the number of weight coefficients that we retain. So if this is a one layer, let's say, of the neural network, we drop a percentage of weights, of the non-significant weights, and it's a good question of how you decide which are the non-significant weights. We have a lot of detail in this work on how to decide which weights to drop. But the best way to look at this figure is starting from this point and onwards. So this is the performance you get with a full neural network. And as I said, this is performance that's competitive to optimal, let's say, detectors. And this is what happens once you start reducing the percentage of coefficients you retain. So you're reducing complexity, you're reducing memory consumption, right? From 100% all the way down to 50%, let's say, without any performance loss. So we're using half, let's say, the network, or 60%, between 60 and 50%, we see no reduction in performance. And then on, you see a scalable trade-off. So this is where you can explicitly trade off complexity and performance of your detector based on a neural network implementation. So you trade off further complexity reduction with a worsening in performance. So, again, we're looking at the aim of this is to look at, if you were to implement this approach, how in practical systems you would implement the neural network and how you can save complexity and trade off performance. So this approach involves, reduction, as I said, in complexity, in memory consumption, and looking towards hardware-friendly implementations of such receivers. That will become important, I think, once we start applying these ideas in practice. The next bit of work, again, under the same context, is we're now shifting our focus to the precoding. So again, you have the transmitter. So this scenario is probably more appropriate to downlink communication, where you have the base station transmitter transmitting to a number of users. And here you would typically have precoding, so shaping your signal to basically tackle the impairments of the channel. So your information signal, precoding, and this is your output signal. And we want to replace known precoding techniques. And here's again a list of precoding techniques. They can be optimization based or the sphere encoding. So the opponent of sphere decoding. So stuff you do at the transmitter. Nonlinear, other nonlinear approaches like Thomson-Harashima precoding, or low complexity linear zero forcing and MMSC precoders. And we want to see how we can replace these with neural networks, again, with an eye on reducing complexity. Again, we're not trying to outperform, we're trying to match performance. We have good performing, classical approaches. We just want to match performance, but reducing significantly the complexity, and again, making these hardware friendly. So more specifically, here we're basing this on a specific family of precoding techniques. So symbol level precoding. This is an area that my team has been working on for the last more than 10 years or so. I'll go very briefly of what this is about. So again, we're looking at a scenario, a downlink scenario. You have one base station transmitting to a number of users. Precoding happens here. And with the knowledge of the channels of the users and the data you want to transmit, you can actually characterize the interference between the users, right? And you can predict the constellations that the users are going to see. And looking at classical constellations, so here's an example of PSK constellations, but you can use for other constellations. The observation here is, if let's say BPSK, for the example of BPSK, if this is my decision threshold, any interference that pushes me away from the decision threshold is actually constructive. It helps my signal move away from the decision threshold and become more robust to noise and outside interference, right? So symbol level precoding techniques, you might see this as constructive interference techniques, are all about taking advantage of this phenomenon. And we've seen in the past 10 years, significant gains with respect to classical optimization-based techniques, so block level precoding versus symbol level precoding. These are highly energy efficient, and we've seen that you can reduce probably you won't see this very well. This is essentially the transmit power to achieve a certain SNR at the receiver. And you can see a gain of almost an order of magnitude, so 10 times less power for the same performance. And how does this happen? It happens by exploiting the constructive interference, basically making use of the interference between the users because you have knowledge of this interference over here. Now, the problem that we're looking at in applying learning is an optimization-based approach for symbol level precoding. And if you look closely, this is a power minimization approach. So we're trying to minimize the power. And here's a constraint. I won't go into the detail, but it relates to the geometry of the constellation. So this is a constraint that enforces constructive interference, basically. And you can see this is a function of the precoders. So the precoders here are W and the channels, right? So one of the interesting ways to apply learning here is, again, with an eye of reducing complexity, you can solve this classical optimization, the power minimization, with iterative techniques, sorry. Let me go back. So with iterative techniques, and one of the classical learning approaches to apply when you have a complex optimization is designing an iterative technique and then unfolding, using deep unfolding to represent the iterations that you use to solve this optimization with network layers. And that's an interesting idea because once you have a number of network layers, like the example over here, each layer represents an iteration in your algorithm. You can actually run these in parallel. There's plenty of parallel processing solutions to implement, neural network architectures. So again, you can reduce complexity and computational time and latency and so on. So first step is taking this optimization, the classical approach, and reformulating it here a little bit. I won't go again into the mathematical details, but the main idea is using the Lagrangian of this problem, designing a new loss function. This is what we're doing here. Here's a loss function tailored to exactly what we want to do in this communication problem, and unfolding the iterations of solving this optimization into a number of layers. Again, I won't go into the details of the architecture here, but the main idea is that we're employing a deep unfolding processing over here. The second thing we want to do, again, with an eye on practical implementation, is see what happens once we have the weights of the neural network, the weights at each layer, and what happens when we start losing precision. So, when you have the weights, you can never, obviously, you can never represent them when you're doing digital signal processing. You can never represent them with infinite, let's say, accuracy, right? You'll have some sort of quantization. So typical approaches use anything between 8 to 12 bits per weight, and that gives you good accuracy, good resolution. We want to see what happens if you start reducing the resolution here. And we apply these three types of quantizations. First of all, binary. So these are the weights now of my network. So we have plus and minus 1, depending on whether the weight is positive or negative. Ternary, which is a classical approach for neural network design, where you have plus, minus 1, and 0. So plus, minus 1 when the absolute value is significant enough, and 0 when you have a very small absolute value, less than some threshold. And the other approach is the stochastic quantization approach, where we quantize, again, binary or ternary with a certain probability that depends, again, on the value of the weights. Again, I won't go into too much detail, but you can find, again, the detail in the relevant paper. So we start off with a full precision weights. So this is a representation of weights in our layer. And we start quantizing a percentage of these, again, with the eye of reducing low bit representation, reducing memory consumption, reducing complexity, and making these hardware informed. Okay. So some characteristic, let's say, results. So first we look at the transmit power. Remember, our initial idea was to minimize the power, so power minimization approach with SNR threshold that will give you the quality of service for the users. So we have two benchmarks here. We have, first of all, the conventional block level precoding, a classical power minimization approach, not using the concept of constructive interference, and the symbol level precoding. So the one obviously that performs much better, so much reduced transmit power compared to the classical block level precoding. And in between here, all these lines represent the learning-based approaches, the performance of the learning-based. So first of all, the blue line, which very closely matches the classical symbol level precoding approach, is the one with infinite precision, right? There's no quantization. And the rest are what happens with binary, ternary, stochastic binary, and stochastic ternary quantization. And you can see as you basically reduce your precision in your information, you start losing a little bit of performance. Again, a scalable trade-off between complexity, memory consumption, and the bottom line performance, which over here is the transmit power. And let's look at the complexity, again, in terms of the execution time. So here we have the symbol level optimization-based approach. So this black and green lines represent two variations of that. I won't go into the detail again, but this is the classical optimization-based approach. This is the approach with a full precision neural network, and these are the approaches with a quantized network. Again, you can see up to, let's say, 2 or 3 times reduction in complexity with respect to the optimization based approach. So again, here you have a scalable trade-off that you can control by tuning the percentage of the weights that you quantize and tuning the number of bits you use between the complexity, the memory consumption for your training, and the bottom line performance. And that's it in terms of, let's say, the hardware informed solutions. Now, the other area that I want to talk about is using learning-based approaches in vehicular networks. And in particular, I'm going to talk about this emerging area of integrated sensing and communication. So let me spend 1 or 2 minutes explaining what this is about. So integrated sensing and communications, to my observation, is an evolution from looking at coexistence of different communication systems with radar systems. So as we release radar spectrum to communications, there's many scenarios where communications and radar will coexist in the same spectrum, in the same frequencies. So there's plenty of research on how to tackle interference between them when they're separate systems. This type of research is going one step ahead, where you want to integrate the communication services and the sensing services through one transmission, one device that does both communications to a number of users, but also sensing targets. And ultimately, having a unique infrastructure that provides not only communication services, but communication and sensing. So if you look at, let's say, if you imagine a smart city scenario where you have such dual functional access points that are capable of both functionalities, if you imagine these being deployed on top of lampposts and so on, you can have a network that not only does communication, but senses the environment And this has a wide range of applications, from infrastructure monitoring to security to incident detection, detecting accidents or incidents on the streets or in the environment, and obviously applications in vehicular scenarios, where perhaps you want to combine radar functionality, let's say anti-collision sensing, with vehicle-to-vehicle communication, vehicle-to-infrastructure communication, and so on. And one of the key benefits in integrating sensing and communications, that from my observation, is that you can again trade off the radar performance and communication performance. So here's a typical example where you have a typical radar metric, so probability of detection of a target sensing something, with communications achievable rate. And for a number of scenarios, by tuning weights in the way you design your system, you can go from full radar performance, full communication performance, and all the points in between. And I think that's one of the very interesting use cases for this kind of approach. Now, we here focus on the vehicular scenario, and we want to show how sensing assists in reducing overheads and involved in the communication, the vehicular communication, and then how deep learning can be useful in these scenarios. So let's look at a communication only based approach. How does this, how is basically the link set up? How is the beam tracking achieved? Here you have a roadside unit, basically a base station serving vehicular users. So typically establishing a link and pointing the beams towards the vehicular user involves an iterative process with feedback from the user. Depending on the beam width you want to achieve, millimeter wave, you're looking for very narrow beams. You have to exchange information on the quality of the link and whether this beam is appropriate, right? So you test different beams, originally with wide beams, then the user has to feedback some indicator, either the SNR it observes or a beam index that it prefers to use. Then the RSU fine-tunes the beam, and we have an iterative process where there's a lot of feedback and overheads involved. And there's an interesting trade-off on how wide you want these beams to be with respect to beam accuracy, how long you want to train your beams, with respect to overhead and latency, and with respect to how much time you have left in your frame to do actual data communication. So if this is your frame, you dedicate some time for beam trading and feedback, and the rest of the time you have for data communication. So there's a balance there of how much you want to train, how accurate you want your beam, and how much time you have left, how much resources you have left in your frame to actually do the communication. So you can see that is demanding in terms of overheads. And in some cases, when the channel changes so fast, so the beam direction has to change so fast, you can actually have this process breaks down and you can have significant outages in the performance. Now, sensing capability is a real enabling aspect in this kind of scenario. So if you have a scenario, let's say, where the roadside unit operates both as a transmitter, a communications transmitter and receiver, and as a radar, you can actually circumvent this feedback for determining the beam directions with by observing the echoes. So when you transmit your downlink signal, let's say, to these vehicular users, you exploit the echoes, so the reflections that come back from the vehicles, to basically detect the direction, the angles of arrival that you need to employ for your next beam, let's say. So using this sensing and prediction, you can then track your beam and follow the vehicular user with minimal latency and keep a reliable link to the user. So as I said, this circumvents the need for this feedback that I talked about, this beam tracking feedback, the need for dedicated pilots in the frame, in the downlink frame, and the errors that are associated with this feedback. So quantization errors, obviously you want to feedback information, you have to quantize it, or the errors that come with receiving this feedback. And another key advantage is where before you had part of the frame dedicated for training and part of the frame dedicated for data transmission, because now you're sensing all the time, you can use the whole frame for data communications and the whole frame for sensing and tracking through this integrated sensing and communications. And that gives you significant gains, match filtering gains in your beam tracking approach, so your sensing performance as well. So here's a typical scenario. Again, plenty of math here, but I won't go into the detail. But you have roadside units and a bunch of users. You can use straight transition models and Kalman filtering approaches to track the beams using the sensed information. So here's a typical example. So a Kalman filter typically employs a state transition model and an observation or measurement model. Here's your state, X over here, and the state in terms of sensing can employ a number of parameters like angles of arrival, distances, velocities, or reflection coefficients, essentially the radar cross-section, a typical metric, let's say, for radar. And through the measurement model and through processing the received signal, so the received echoes that the radar senses, you can extract round-trip delays and Doppler offsets that will give you distances, that will give you speeds, velocities, and angles, right? Through a process of processing your received signal that I won't go into the mathematical detail right now. Now, this is all fine. You can use classical non-learning approaches like extended Kalman filtering if the scenarios are relatively simple. So if you have, let's say, one vehicle going in a straight line, okay, you can let's say model this with simple kinetic equations. But once you have many vehicles, complex trajectories, turns, and so on, this becomes mathematically intractable. And this is where there's scope to apply learning-based techniques. And here's an example that you can find the details of in this work, where we use a Bayesian approach, where basically we want to maximize the a posteriori probability based on our observation, so the received signal, Doppler shifts, and delays, to predict or estimate the radar parameters, the sensing parameters. And in particular, basically the angle of arrival will tell you basically where you need to point your beam, right? And we use a factor graph approach here that I won't go into the deep technical details, but we've seen that through training, this can actually tackle a scenario that you couldn't really tackle based on a strict mathematical model-based approach. So one indicative result in a key scenario. So here we have a roadside unit and a vehicular user that is moving towards this direction. So crossing essentially the direction of the roadside unit. Obviously, if you think about it, you have to point the beam to the vehicle as it crosses through. And once the vehicle is close to the area of the roadside unit, the beam changes become very fast, right? So let's see what happens. So here we are looking at the achievable rate versus the time. So as the vehicle moves towards the direction of the roadside unit, and we compare three techniques. One is a comms only based approach, so without the assistance of sensing. So, and this is an extended Kalman filtering approach. One based on beam training, where you have feedback from the vehicle, and it basically selects between a pair of beams for each time instant. And one based on this dual functional radar and communication approach. So first thing you can see that the beam training approach based on communication, you have a good achievable rate up to some point. And once you are close to the area of the roadside unit, when the directions change very fast, you have a breakdown here in the communication. Basically, you have an outage because the beam training cannot keep up. Because you're only using a pair of beams, the beam training cannot keep up with a fast changing beam direction. So you lose, essentially you lose connection. Here's what you have with an extended Kalman filtering approach. So an approach that uses observation and prediction. So you can maintain communication, but with a limited performance. And here, the sensing capability gives you a much improved performance where you can exploit, let's say here, the reduced distances, right, from the roadside unit to keep increasing your achievable rate. So here's an example where the sensing capability is actually very useful in maintaining a link with good quality. And these are some more results in a more complicated scenario where we have a larger number of vehicles. So a more complex scenario where we've used this factor graph approach. And first we have the misalignment probability. So the probability that the beams are misaligned between the vehicular user and the roadside unit. And you can see, so here we have the blue lines represent a low speed vehicle, and the red lines represent a high-speed vehicle, and we have varying beam widths. So obviously, with a very narrow beam, if you're aligned, you have much better achievable rate, but it's more challenging to align, right? You have a higher risk of misalignment and outage. And with a wider beam, you're more likely, it's easier to align the beams, but with a more limited achievable rate. And you can see this effect here. So the misalignment probability is higher for the narrow beam and lower for the wider beam. But these are all results that are generated from a learning-based approach in a scenario where we cannot really design a good model-based approach. And this is the sensing performance, so the vehicle tracking performance, and one of the parameters is the angle. So we're looking at the error of the angle and the CDF, so the cumulative density function of that. And we're comparing extended Kalman filtering, so without learning, one feedback approach, and this factor graph-based, learning-based approach. And you can see that the factor graph-based approach, the red line over here, has the best performance, where you have higher probability of small angle errors compared to other approaches. So again, benefiting both radar performance, so tracking and let's say localization of the vehicle, tracking the parameters of the vehicle, and the communication performance, where here the learning is an enabling aspect here. So it enables you in scenarios where you would lose connection to actually maintain a resilient link. A final couple of things I'll go through very quickly. So one scenario is we're looking at fixed wireless access links and using learning to predict beams. So we've observed that this is a particular challenge for industry, where you have, so the scenario here is fixed wireless access. So having access points deployed on tops of lampposts or on building walls and so on. So one of the key challenges is these are typically using millimeter wave links, high-speed millimeter wave links with very narrow beams. And one of the challenges is to keep these beams aligned. So many small environmental perturbations like vibrations from traffic or wind can really mess up the alignment of the transmit and receive beams because the beams are so narrow. And a key challenge here is how to adapt when you have transmitter and receiver moving, vibrating, how to adapt the beams so that you're always aligned, right? So without learning approaches, it's very difficult to predict the beam and keep the alignment. So the approach here, we're adopting a learning-based approach, and we're adopting vibration models where you can see the elevation angle, how it needs to change depending on the vibration. And the key here is we're merging these vibration models with the communication scenario and the geometry here to keep the beams aligned. Again, a complicated problem to solve analytically because of the complicated geometry, and something that the learning-based approach can help with. And we want to do that by limiting the training as well. So that's one of the challenges that I highlighted at the beginning. So how to do this with a relatively small number of training samples. And here's an indicative result. So again, we're talking about the successful alignment probability here. So how well the transmit and receive beams align versus the number of training samples. And here are some benchmarks, and you can see that all of them achieve reasonable performance, but with a higher, with quite high number of samples. And these translate to latency. And here is how the learning-based approach using this modeling performs with only a limited number of channels, so orders of magnitude less samples than benchmark approaches, and close to full alignment most of the time. So better alignment and with a reduced number of samples. Again, very quickly, I won't go into the details. You can find them in the relevant paper. And a final bit of highlight where I think it's interesting to apply a learning-based approach is this concept of joint precoding and channel specification. So especially as we go towards large antenna arrays, channel estimation is an important challenge. And there's lots of work going on in reducing the representation of the channel, reducing the dimension of the channel, the dimension of the channel you want to estimate. And in this work, we want to come up with a technique that at the same time jointly comes up with a transformation of the channel represented by this matrix here that reduces the dimension of the channel, so projects the channel in a lower dimension space, exploiting the sparsity of the typical millimeter wave channel, and at the same time design the precoding approach. And here again, for the precoding approach, we use the symbol level precoding, so the constructive interference precoding that takes advantage of interference between the users. So the learning-based approach is an enabling thing here that allows us to do two things at once: design our precoder and design our channel specification matrix, essentially again saving in the training of the channel and the overheads of the channel. Again, a representative result. Here we show the throughput, or good put. So this is a key metric that basically captures the trade-off of increasing your training and spending more overheads, a larger overhead to train your link, and the bottom line performance, error rate, and block error rate, and so on. And we do that in a scenario where we quantize the feedback of the channel, and we plot this again with the number of quantization bits we use to represent the channel. And here are some benchmark techniques that are based on precoding approaches with full CSI. And here are the techniques based on learning, where we jointly optimize precoding and channel specification. And you can see that we clearly outperform. And there's a trend where your performance increases as you increase the number of quantization bits. And then it either saturates or it actually reduces, because the more bits you spend, the more overhead you have, and the less resources are left to actually push your communication through. Again, an enabling scenario where learning-based approaches can help you solve complicated problems. I want to finish off by highlighting a number of research directions, again, focusing on the context that I set up at the beginning. So looking at complex problems that either the modeling is inaccurate, we don't have good models for, or problems where we have good modeling, but it's too complicated to solve analytically. I'll only highlight a couple of directions. There's many out there, but these are some observations. So first, an observation from a project that we're running on energy autonomous networks. So this is a large European project where we're looking at scenarios where you want to design portable networks that can operate outside the power grid. So either in disaster scenarios where you don't, let's say the power grid has been damaged, or remote scenarios where it's not convenient to plug things in, or on-demand scenarios where, again, it might not be convenient to plug in and out base stations, and so on. And these have to be portable. So we're looking at easily deployable small base stations, or also base station mounted on UAVs. And the key here in this area is the integration of the communication design with renewable sources, energy harvesting, and energy storage, so battery modeling. And I would invite you to find out more about this project if you're interested in this area on our website. So what are some key open problems here? Obviously, I hope it's clear that you have to achieve an energy autonomous network, you have to combine and balance the consumed energy in a network for communication purposes with the energy that you harvest from the sun or from the wind or from renewable sources, and the energy you store, so the capacity of your batteries and so on. So these, already the communication problems are complex enough. Now, once you integrate with harvesting and energy storage, you often have complicated modeling of batteries, photovoltaics, or wind harvesting. And the integration of these models into optimization problems are very challenging. And I think that's an area where learning-based approaches can circumvent all this complex modeling. The other thing, as I mentioned, the portability here involves UAV communications. And another interesting area, I think that's relatively open, is the trajectory design, not for communications only purposes, but adapting energy consumption, energy harvesting, and energy storage. So trajectory adaptation based not only on communication metrics, but also energy, navigation, control metrics, integrating with sensing when you have swarms of UAVs and you want to make sure that they don't collide, for example. And again, online approaches like reinforcement learning seem promising in this area. And a final area that I think this, learning-based approaches, it's a wide open area for applying learning-based approaches, is this area of integrated sensing and communications. Again, you have a transmission, a device that sends signals that are good for, that carry information for users and are good for target tracking. So have good properties like correlation properties, ambiguity functions, typical metrics for radar performance. So a number of open problems here involve complex problems where you obviously here you want to integrate communication metrics and sensing metrics and communication operations and radar operations. So when you design joint metrics, these can be quite mathematically complicated. So again, plenty of space to apply learning-based solutions. Or when you have complex scenario, we saw a glimpse of that in our examples for vehicular communications, many targets, complex trajectories, or complex geometries of the targets or of the scenarios. Again, there's plenty of scope in designing such learning-based approaches. And a wide open area is the receive processing of these ISAC signals, so integrated sensing of communication signals, where you now want to design a receiver that both detects information, so communication signals, but also detects or tracks radar parameters. And again, already there's plenty of learning approaches in radar signal processing for classifying targets, for tracking and predicting target parameters. Once you integrate this with signal detection techniques, where already, again, when the comms only literature, there's plenty of learning-based approaches, you have an area, a space with very nice, interesting trade-off problems that learning-based approaches can provide significant solutions. So with that, I think I'll end. Here's a list of all the relevant papers that were involved in this presentation, and I think you'll get the slides of this talk. Before I end, I want to thank the people that actually did this work that was presented today, the members in my team that involved in these works. And I'd like to thank you for attending. I'd be happy to welcome any questions, and I'll try to answer to the best of my ability. Thanks very much.
Thank you so much for the nice presentation. I think in the interest of time, I would just like quickly to invite Vishnu for the Q&A.
Thanks, Thomas. Thank you. And thank you, Chris, for that exciting talk. I think we have seen before about learning mechanisms, applying and so on, but I think this is the first time that we are hearing about a niche overlap, which you correctly pointed out. Not much time, but I want to take some questions which are quite interesting. India is asking share slides. Yes, India, it will be there in the same link. Abdurrahman is asking how and why does deep unfolding give a performance gain? I think in one of the slides you had shown, Chris, about this comparison of performance between DL-based approaches and classical approaches. I think this question is related to that. What is your comment, please?
I don't think we showed deep unfolding outperforming. Let me see if I can share the slides again, and maybe you can point me to the right slide. So deep unfolding is involved in this slide over here. So this is where we use deep unfolding, right? For the symbol level precoding, and the results we showed here are pointed here. So this is basically the technique that we want to emulate, right? This is the optimization-based symbol level precoding, right? And we're showing the transmit power. So this is clearly the best performing technique. So that it has the minimum transmit power, right? It's a power minimization approach. So none of the techniques based on unfolding outperforms it, but what we actually achieve is this significant complexity reduction. And once you have, this quantization, the significant reduction in memory consumption and computation. So yeah, to the best of my understanding, you will never outperform an optimization by using deep unfolding, but you can actually reduce the computational time. You can implement deep unfolding in parallel processing. So that's the gains that I see in this scenario.
Yeah, I guess that was the question. I hope that was the question in terms of when you say optimization. Actually, there is a similar question, and so is asking, when you do quantization number of parameters from a layer, then how does it matter if you consider the tensor nature of processing when you use GPUs? So I guess the question is that if you consider the tensor nature of processing, can you still get benefit by reducing the number of parameters?
I mean, I don't think we went into that deep design of neural networks, so changing the actual architecture and the tensor processing. But for a classical tensor architecture, we started reducing the precision of the weights, right? That's all we did. And I think this will have gains, so the gains will persist in a number of implementations and architectures. But I mean, we haven't tried it, so I cannot really, tell you something more specific here.
Thank you so much. Let me take this one about from Mohammed. He is asking explanation on how to apply DL to different features. I think you covered some of them today, but he's asking RSRP, RSRQ, and so on, and the 5G channel quality model. Specifically, he has listed out delays and latencies.
So the question is where learning-based approaches are useful with these scenarios or metrics?
Right. Yeah. I guess the question is that in general, how to apply such techniques, and whether it is useful.
Yeah. I mean, I think this reinforces what I'm saying here in these slides. So I think one of the interesting areas that I haven't seen, explored that much is, once, all this hype, calms down and we start implementing a lot of these approaches on practical systems, complexity, memory consumption, and computational time will be important. Computational time translates to latency, right? So you want to be able to come up with techniques that reduce the memory footprint, reduce the computational time. And I think looking at implementation informed design of neural networks, like we're doing here, for example, this is just one example where you look at quantization, where you look at reducing the number of weights and making the implementation more efficient. These will become important. And I think, yes, they will translate to real, bottom line performance metrics in 6G and beyond, like latency and, other quality of service metrics.
Thank you, Chris. Maybe one last question from my side. I think you did talk about mobility, and I mean, its implications towards the end. You were about slide 28 or so. You were talking about fixed wireless, whereas in the beginning of your talk, you were concentrating, or rather, did not touch upon this aspect. I want to generally ask you that what are the implications of handling mobility with such schemes? What kind of complexity does it add? That do you need further study into that area? Are there models which already exist, or these techniques will apply as it is?
Yeah, I think that's one of the areas that I think are very promising when you want to apply learning into high mobility scenarios. These are the challenging ones. These are the ones that typically have large overheads to establish communication and difficult to optimize, difficult to design. And I think we saw some examples today that learning can actually, by exploiting sensing in the scenarios that I showed, and using prediction, you can actually minimize, the time it takes to adapt a beam, let's say. So high mobility scenarios, they're a very good candidate, I think, for applying learning and prediction, right? You don't have the time to respond or to run an optimization. Prediction is going to be a key thing. So I think that's one of the key areas where you want to look into the research of applying learning techniques. Yeah.
Okay, thank you very much, Chris. I think thank you for staying back, and I think majority of the participants are still here. That means they would like to hear from you again, I suppose. And these are interesting topics. I'm sure we would like to track what you're doing, and we would like to read your papers in future. Your future directions are quite interesting as well to us. Thank you very much for staying back and answering all the questions. Back to you, Thomas.
Thank you very much, guys, for inviting me. This one has been a pleasure, and I hope I can, keep in touch with your, initiative over here. I think it's very interesting.
Thank you so much, Chris. I think it's been wonderful to have you in one of the webinars for the ITU and Machine and 5G Challenge. We really appreciate you making some time to join us and to be with us to make this interesting presentation. So we hope that you'll be in touch and we can maybe interact on different aspects of the challenge. So thank you so much.
Absolutely. Thanks, everyone.
I would also like to take this opportunity to thank everyone for attending today's episode in the webinar series that is organized by the RTU AI and Machine and 5G Challenge for your lively participations and questions. We have more webinars sessions that are coming. The information has been shared on the event page as well as in the chat. So please register for the upcoming webinars as well as for the upcoming events. Please check the schedule on the challenge website as well as on the AI for Good event page. I'm looking forward to seeing you in the next episode of the webinar series. From me and my colleagues at the ITU AI and Machine and 5G Challenge, I would like to wish you a very good day